Welcome back again. Now let's move on to our next speaker. I am delighted to present Professor Margarida Telo da Gama from Lisbon University. She is a renowned expert in interfacial and surface phase transition, especially wetting transitions, the structure and phase diagrams of soft matter, thermodynamics, and the kinetics of patchy colloids and liquid crystals. And today she's going to speak about non-equilibrium interfaces. Margarida, please.
Hello, thank you very much for the introduction and thank you for the invitation. It's a real pleasure to be in Granada, even if I'm not in Granada, but in such a company. I cannot really, I almost got cold feet, but you know, one has to do what one has to do. So as Paco said, my main interest has been interfaces of one way or another. And of course, I started from equilibrium, but Paco is responsible for starting me into non-equilibrium interfaces. And I don't apologize, but I'm going to make a detour, and I really want to refer some of that work because, in fact, in those days, I learned a lot. And in fact, some of the things I'm doing today have some connection with that work. So interfaces and surfaces, this is something from Philip Paul on one of his books, of his many books. And he says that they seem to be, well, there is some prejudice against surfaces because they deem to be superficial and so on. And I put this here not just because Philip said it, but Philip was a student in Bristol after me. And I would like to make a small tribute to the places I've been and where I've learned some of the things I know today. Okay, but then Philip continues. This is not justified because surfaces and interfaces are the seat of a variety of fascinating phenomena. And this is a quote from a book by Rawlinson and Widom that came out just as I was finishing my PhD thesis. And so Widom is here and Rawlinson, and now I have lots of pictures in front of the people, but this is Widom, this is Rawlinson, and this is the younger version of me. And my boss should be somewhere here, who's Keith Gubbins. And so that's, I ended up at Cornell and I continued to work on interfaces. So what did we do? I'll start just with a very brief couple of slides on equilibrium interfaces. They were really starting to get the attention of a lot of people in those years. And I was pretty lucky to be in the right place, both in Bristol and then at Cornell, where lots of people were studying interfacial phenomena. And as Paco was saying, some interfacial phase transitions, the most well-known of which is wetting. But let's start from the beginning. And if I think of interfaces, one of the most important and useful concepts is that of surface tension. And this can be thought of in equilibrium as an excess free energy. This is the Gibbsian version of surface tension, or as a force, a tangential force per unit length. This is even older, before it predates these thermodynamics, things by Young and Laplace and so on. And there are some pretty pictures here from, if not from Wikipedia, but from the internet. I tried to give references wherever I could, but it strikes you as something that you see every day, and sometimes you don't think very much about it, but in equilibrium, this is more or less understood. But when you go to a non-equilibrium systems, some of these concepts are very hard. Maybe they don't even exist, or maybe we don't really understand them. And so this is going to be a bit my effort today to try and convey what I don't know, what some people are trying to understand about these systems. Okay, so let's go a little bit. This is a macroscopic version, as I said, some dynamics. Let's go a bit more microscopic. And if I go a little more microscopic, I have to go back to van der Waals. And van der Waals was the first to recognize that between a coexisting liquid and vapor, or two coexisting phases, there would be a region, a transition region, where the properties of one phase would go to those of the other phase through a distance, which is typically the correlation length. Of course, van der Waals didn't put it in this language, but his theory actually predicts this. And this is a mean field theory, as you all know. And so the next thing I want to say as a sort of historical contribution, which was very important, is many years later by, it's here, Buff, Levitt, and Stillinger, that recognize that an interface is never really flat because there will be thermally excited fluctuations. And so the picture is more like this one on the right, where you actually have some interfacial fluctuations, which are excited by the temperature. And at equilibrium, we know almost everything there is to know about these fluctuations. And in fact, I would say that these two pictures, if you try to reconcile them, of course, this is a long wavelength picture, and this is something that totally ignores fluctuations. So people are getting into trouble, even in equilibrium, when they try to measure things at very small or very large Q and try to define the intrinsic or the mean field type of interface. This is something that is still going on today in just at the basic level of characterizing it, trying to reconcile two different pictures, which maybe you shouldn't try. I mean, theories are always, they work under certain limits. They don't have to go very smoothly from one to the other. Okay, so really these are the two topics of the talk, and then Paco more or less said it. When you have an interface like this one, you would like to know if it is rough or if it is smooth. In other words, how do these fluctuations behave as you look at larger and larger systems? And also the other thing you'd like to know, you've seen it in the first pictures, if there is, for example, a fluid in contact with a solid, what is the contact angle? Does the fluid spread? Does it not spread? Does it wet or does it not wet? And so these are the two questions that I want to revisit, going from the equilibrium situation where I think we know quite a bit, and these were very hot questions when I was finishing my PhD, to what can we say now under non-equilibrium conditions. So if I talk about non-equilibrium interfaces, I have to mention the Cardar-Parisian-Zhang equation, and I don't want to I mean, this is a busy slide with many equations. It's the one with most equations. I'll refer back to it when I need, just to define some of these exponents if I have to. But basically, this is a dynamical equation for the height of an interface, and it varies with time. And this is governed by a linear term, which is diffusion like. This is like the surface tension that I was talking about, and by a non-linear term and some noise, okay? And so this reflects the fact that under non-equilibrium conditions, you can have, the interface can grow in one direction, but also in lateral directions. And this equation is going to pop up several times, or at least results from this equation, with or without the bounding surface or substrate. And this is where Paco comes in, and Miguel Angel a little bit, because I had been working on wetting for a while, and people had been working on the wetting transition, which is something different and much more delicate. And Paco wanted to know what happened if you actually did that under non-equilibrium conditions. So if you have a wall, and if you have an interface, and if now this interface, the dynamics of this interface is given by the, for example, Cardar-Parisian-Zhang equation, how will that behave? How does that compare with the results that people knew at that time from the equilibrium studies? In equilibrium, you just drop the lambda term, so you have some potential, and so the dynamical equation becomes something very simple. This is the surface tension or something related to it. And this is the chemical potential, this is the noise, and this is the potential, the binding potential, which can have different forms. And of course, it has to have a minimum to bind the interface. And then the question is, does it unbind? And under what conditions does it unbind? And this is at equilibrium, the wetting transition. And it's been subject of a lot of work. And I'll just show you a very, in one slide, more or less a summary of what happens. So if you have something droplet of liquid that partially wets a solid by changing, for example, one of the fields, the temperature, this fluid may spread completely. And we call these, when that happens, a wetting transition. It has its own properties, non-trivial, very non-trivial, fluctuations which are non-trivial, and so on. And there is a very similar transition because this droplet could just, rather than spreading, retract. And we call that drying. And under equilibrium conditions, these two transitions are symmetrical. Let's put it that way. So if I look at liquid gas, I have pressure, I have temperature. This is just the bulk diagram. And so I'm looking here at coexistence. So the liquid and the gas coexist. And if I go from that situation to this one, it means that on the coexistence line, there is a wetting transition point, a threshold, above which the fluid does this, spreads, and below which it does not. Of course, there is also above that threshold, I can always approach it from the bulk phase, the dilute phase, and this is a different transition. It's called complete wetting. And I have here the height of the film. This is all equilibrium that I can measure and calculate under those different conditions or paths. So the question that Paco asked himself when he came to Lisbon was, what happens if instead of having the equilibrium stuff, Edwards Wilkinson, if instead of having that, we put the Cardar, Parisi, and Zhang. So we put back the nonlinear term on this dynamical equation. I'm not going to say very much about it, but one striking thing is that wetting and drying are no longer symmetric. There is an extended coexistence region for wetting. This is for a lower interface. I'm not going to be able to explain all the details, but this does not happen for drying. So for example, this looks very much like, just on the line and superficially, looks very much like the equilibrium phase diagram. This one is clearly different. This extended coexistence region between pinned and moving phases is something which is very characteristic of non-equilibrium systems. It's related, and you can ask Miguel Angel, and I'm sure even yesterday Hans was broaching something about it. It's related to all sorts of other phenomena, from percolation, from directed percolation to synchronization and so on. I have no time, it's fascinating, it's very hard, very complicated, but because Paco is Paco, so he actually calculated the exponents. And of course, these exponents are also different. So not only the phase diagram looks different with a very extended region of phase coexistence between two interfacial phases where pinning and moving interfaces coexist. And I'll show you some pictures again from Paco's work. This is in 2D, and this is for wetting, and this is the reason why they coexist is that these fluctuations, there is a mechanism for these values, negative values of the nonlinear parameter that will dampen down those fluctuations. So you have bits of the interface that dip in and others remain like this. So this is a 1D example, which is maybe clearer to see. This is the time evolution. This is just the boundary. And here there's a plot where you see these things. These things are very cusped, and this mechanism only works if lambda is negative. It doesn't work if lambda is positive. And this is why you have the different phase diagrams. Okay, so my thanks to Paco and to Miguel Angel for introducing me to such a difficult problem. And it is a difficult problem. It's difficult numerically, it's difficult analytically. They know a lot more about it than I do. And I just want to make this reference because this is how I ever started looking at non-equilibrium interfaces. There are some references here. They're a little bit old, but not as old as the original references for the equilibrium wetting. Okay, so this is like an introduction. Much more recent work, which is kind of related in some sense that I'll try to specify and to highlight in what follows, is we've been looking at the properties of interfaces which are far from equilibrium and which can be modeled by colloidal particles with patches. Paco mentioned that at the beginning, that one of the topics that I worked on and we had been working on first, again, at equilibrium, now non-equilibrium due to other people, and I'll acknowledge them at the end. It's these patchy colloidal models. But I want to start with something borrowed. So something that caught my attention. There was this Nature, again, 10 years ago, of the coffee, the coffee ring problem. And I don't think I have time to run all the, no, this is only a picture, I'm sorry. So I don't think I have time to run all these films. You can find them in the net. This is the beautiful, and you see a coffee ring here, which you would more or less expect. And so the density is very homogeneous, and the colloids sort of accumulate at this boundary, this surface or interface, if you like. And this is why the stain can be seen. So far, so good. I'm sure all of you have made colloidal or coffee stains or other stains. But what was kind of amazing was that these people in this paper, this one doesn't have too much. Let me show you this one. So they actually filmed, because that's the beauty of colloids. They actually filmed, and they could see how the coffee ring stains were made. And they discovered something else, which is interesting, very interesting. So this one, I don't want to go. Okay. So in summary, these people changed the shape of these colloids. So this is not coffee. It's not coffee beans, or coffee, grounded coffee, but they were colloids. They could control the shape of the colloids quite precisely. And this is just a scheme of the drop. The drop is evaporating, so it's clearly non-equilibrium. There is, these particles are driven to this interface. Forget how they're driven. We just assume they're ballistically driven, and then they deposit at the interface. So far, so good. There are many, many ways of looking at the coffee stain problem. But what came as a surprise, I think, in this paper and to the authors, was that by changing the shape of the colloids, here they're all spherical. But if you look here below, these are actually little spheres. These are more like little fat ellipsoids, and these are thin needles or ellipsoids. And they saw that the edge of that interface, so the roughening of that interface, changed as the colloidal shape changed. And in the intermediate regime, they actually looked and they measured experimentally, and they found a scaling roughening of the interface, which belonged to this Cardar-Parisian-Zhang interfacial scaling or roughening. But then as they made these needles more and more thin, there was a transition unexpectedly to the quenched Cardar-Parisian noise class. Okay, here it's just different. If they're spherical, this is really just the roughness is even different. But this was well understood. This was a bit of a surprise. And so these are more pictures from the experiments. And so we have the two limits, spheres or almost spherical, and ellipsoids. And for the ellipsoids, what you see is that here everything is sort of compacted, and here there are chains that are formed. Chains, I mean, these ellipsoids try to sort of go next to each other, and they form these chains. And chains, as everybody here in Lisbon knows, something I've been struggling with and sort of thinking about from the days of the dipolar systems. But the experimentalists also noticed, because they actually did the experiment with and without surfactant. So if you add surfactant to the water that they used, what happens is that you reduce the surface tension. And this chain behavior disappeared when you added surfactant. So clearly, these interactions are capillary interactions, and they're driven by the famous surface tension. And if you make the surface tension very small, nothing very much happens, or nothing very different happens between the two extremes, okay? So here is something that Cristóvão and Nuno, but certainly Cristóvão, did. So this is experiment, and this is, we try to model these particles and simply try to calculate the interactions side to side. And this is the branching, or if you like, this is one chain that is sort of at an angle, perpendicular or whatever, to another chain. So the main interaction seems to be the side by side, which you would expect, but then for certain values of the surface tension, you also promote these chains branching. And this seems to be really what is the difference between these types of behavior at the interface. To cut a long story short, okay, so we knew how to calculate these interactions, mediated capillary interactions, because Deryakin told us how to do it. This interaction scales with the curvature of the ellipsoid in this case, the distance between them, and even these people have actually worked it out. And so we plotted the energy landscape of these colloidal particles, and it's little, you find lots of little minima and big minima, but then we had to simplify it because we had been working, as I said, with these simple spheres that had poles on it, or patches. And it was quite clear that the physics is that you have two main attractive mechanisms. The one side by side, it's driven by some probability of binding, and then the head to tail or pole to side or junction, which is a weaker one. So again, well, here is what you expect. So you can plot the whole energy landscape, and it's kind of complicated, but then you can sort of, using these techniques that you borrowed from other work that Nuno did, watersheds and so on, we could relate the probability of binding to the size of the attraction basins of two the most important configurations. Well, so we had to define the basins and so on. It's I don't have time to go through the details, but once we had that, then we had reduced the problem to something we could do, because we had been working on these patchy colloidal particles that had little sites where other particles could bind. And of course, we could simulate these for as many patches as we liked, with different energies and so on. So again, I don't want to go through the details. All this is work that was published even before we saw the experiments, or more or less around the same time. And so this, just to tell you, we didn't actually solve the dynamics. This is just kinetics. So we had the probabilities of bonding, and we could drop particles one by one. We could see the films growing. This is for something, all the patches are equal. 3 patches, just to check our numerics, I'm sorry. But then we knew from the experiments and from this anisotropic mechanism that made side to side different from pole to side. And even before we did all this complicated calculation that I talked about, we just did some, we ran some simulations by varying the ratio. We only had colloids with 4 sides. This is in 2D, and 2R A, 2R B. The AA is the strong bond, the AB is the weak bond. So one promotes the chains, the strong, and the weak promotes the branching. And we just said, well, let's try and change this parameter and see if we actually see any change in the roughening behavior. Because we tried many other things, just anisotropy, just putting if we don't change the energy scales, nothing happens. Everything is Cardar, Parisian, Zhang scaling. But when we tried that, changing just the binding probabilities, what you have in this paper, and this is 214, we actually saw that as the colloids became more and more anisotropic in that sense, so if the two binding energies, the ratio of the binding energies that then reflects on the ratio of the probabilities of binding increased, we could actually go from the K, so this is the 1, this is Cardar, Parisian, Zhang, and then you could go in the other limit to the quenched Cardar, Parisian, Zhang. This is very still an open question. Why do we observe the quenched Parisian Zhang for such an extended, it's not at one point, it's for an extended region of the parameter space. And on the right, we have the hard work of Cristóvão for a couple of years to try and make our little model match the experimental capillary interactions here. So no adjustable parameters. And this is what is observed in experiments and the comparison with what we actually can calculate just using this as a free parameter. And we find reasonable agreement. So the mechanism seems to be captured by our small calculation. And also, just as a final check, we calculated the cluster distributions, and they also seem to be reasonably in line with the experimental results. So there is an open question, and we have some ideas, but it's this last paper was actually published with the experimentalists that provided some more data, but this is unusual. Okay, so I want to finish. Let me see how much time I have. 10 minutes? No. 9 minutes? No. Paco, how much time do I have? I even have 26.
Near 20 minutes.
Oh, I went too fast. I can go back. Okay, so let me slow down. It's like the stories of the rivers between Spain and Portugal. When you get to the south, it goes slower. So let me go slower now. So all these two types, one for wetting, one for roughening, actually quite clearly non-equilibrium interfaces, but they are what you might call driven non-equilibrium systems. So the particles themselves are quite passive. They don't, unlike active particles, they don't take energy from the environment at the particle level. And they're driven either because they're away from their preferred phase equilibrium state, or because in the case of the droplet, because it's evaporating, and therefore there is some drive. So there is some external field that drives the interface away from equilibrium. In the active particles, and I have this picture that I call this an active particle, while this is a driven one. And I actually chose these because they're so similar. But Kate gave a wonderful talk yesterday, because we can talk about active particles as physicists going from the cellular or subcellular scale up to meters. And so you have to be careful a little bit. But in any case, so here somehow, if I consider this to be the particle itself has some mechanism of propulsion. And this is not, and here you might say the mechanism is the same, but quite clearly here, this is indicating that this is a drive. So this is not supposed to be very more than just a reminder that I'm going to explain the model a little bit. And I'm going to move now from the driven to the active. But in the previous two stories, the particles themselves, or the fields, they were just passive, and there was some external field or drive. Here, we don't have that. So what happens if you have active particles? And one of the things that happens if you have active particles, at least there are several things that happen, but some of the most striking for me are the appearance of new phases. And one of them is this motility-induced phase separation, and it's illustrated here on the right from an actual paper where you have these self-propelled colloids. And what happens is that they move around when they can rotate, but if they sort of in a situation like this, it takes some time until they rotate away from these, until they can move out again. And there's a positive feedback mechanism, and therefore you can find clusters or even phase separation under conditions where the particles themselves don't have any attraction. So the particles are just repel each other. They have this propulsion, and then when they bump into each other, it takes some time for them to get away. And because this is the more of these particles get stuck, the more others will come into it. and eventually you might get phase separation. The theory for this, at least not exactly for active Brownian particles, but for something, I should be careful, but for the quorum sensing particles has been done by Cates and co-workers. It's a beautiful piece of work. And in that case, you can actually do the coarse graining almost exactly as far as a physicist goes. But in practice, it's more common to find these active Brownian particles that I've been showing you. And this is already, again, you know, almost 10 years ago. So there's been a lot of work on these MIPS phases. And of course, being me, I looked at it and I said, well, you know, if there is a phase or if there is phase coexistence, I want to look at its, well, wetting properties or at its roughness. And this is what work we started. And again, I will tell you a little bit about it in the next few transparencies. Okay, I still have almost 14 minutes, so I can more or less do it relaxed. So again, this is a lattice model. The previous colloidal particles were in continuum, so that they could move around. Here, the particles are on a lattice, and they can do three types of things. So they can move about from side to side, they can rotate, but one of the directions is trying to mimic the propulsion mechanism. The velocity or the speed, if you like, in one particular direction, here in red, is different from the other three. It's larger than the other three. And by the blue arrows, I mean that these directions can rotate every now and then. And two particles cannot be on the same side, right? So the only interactions are excluded volume. And this is the simplest model probably you can think of, and this is more like the mechanism of an active Brownian particle than a quorum sensing particle. Okay, because we wanted to look at the wetting, we had a problem. We wanted to look at how the films grow on a surface at a given density for the bulk. But now we don't have ensembles. You cannot do grand canonical ensemble, you cannot do, and of course you can simulate the bass, but it's a little bit stupid, and in Lisbon we're not that rich, we cannot simulate a big box to have a surface in the middle of it. So we sort of invented some mechanism through which we considered to have a blue region. I know this is violet, but I don't like violet. And so in this region, we actually take away or put particles so that the density of this region is kept constant at a given value that we predetermine. And once they're in that region and everywhere else, they will move with the same rules. This is not dynamics, with the same rules as all the particles. So these are the two systems we used. We used the first one to calculate the phase boundaries, the MIPS boundary, and then we used the second one to look at the films and how they grow as you approach the phase boundary. Okay, so here is some results, or here are some results of the simulation. So what is your control parameter here? Well, we can have a certain density in the box, but you know, the lever rule still works in these active systems. So basically the control parameter, the equivalent to the temperature here is the activity. So by changing the activity from fixed number of particles, so this is a closed system, you can see that there is an activity above which you start clustering, and then these clusters grow. And you can actually, I mean, you can use relatively sophisticated analysis of these histograms, and we can construct a phase diagram, MIPS-like phase diagram. So this is like an inverse temperature, but if you look at this, this is just like an ordinary phase diagram. This is density, and this is activity, and above a certain activity, the system is no longer homogeneous. It breaks into two phases. And of course, the amount of phase that you have in a system like this depends on the overall density of the system. But the bulk densities are just the same. And this is sort of checked here by using different total densities, and the different colors just represent the same result for the bulk coexisting densities. So we were happy. So now we have a phase diagram. And so one is low in density, the other one is high in density. It looks fairly symmetric, but I think there are still some questions there. And okay, so now we have the phase diagram. So once we have the phase diagram, we can put the surface, or two surfaces if this is a simulation. So we put just two surfaces, well separated. And now we switch to the open, to this ensemble. So in this case, we just keep the bulk density fixed through this trick. This is not an ensemble, but it's a trick to maintain the bulk density constant. And we see how the film grows at the surface. And we expected the film to grow exactly through the same mechanism. If a particle, when it finds another one, gets stuck, of course, when it finds the surface, it gets also stuck, and it takes some time to rotate away. So people knew that particles accumulated at active particles accumulated at surfaces. The question is, does this happen at any activity, or can you actually find some threshold, like in the wetting problem, above which this film will grow and grow and grow, and below which, well, it's the other way around because this is inverse temperature. But anyway, it works like the inverse temperature. So what we tried to do, and we did, and for that this was work of a student who's now in Italy. And so we could decide two activities, the plots above and the graphs below, and different bulk densities. And what you see here is that if you're very far away from the bulk coexistence, the film remains finite, which is what you would expect. They accumulate, but there is no drive for this film to grow to an infinite or to a macroscopic level. But as you approach the coexistence, this film height or profile grows. I mean, you can see here there is a flat liquid-like layer at the surface. And it happens that the other activity, and all the activities that we tried, of course, zero temperature here would be infinite activity. We cannot simulate infinite activity. Also, this is a problem of system size, because if the activity is very, very large, the propulsion is very large, so it goes from one. So we have to we have a restriction on the maximum activity that you can do. But as far as you can tell, this is what happens. So we didn't find any transition. And these are just some more plots. I mean, this is just a dynamic. This is the height of the film as a function of time for different bulk densities. And what I want you to notice here is that some of these lines grow with a velocity which is constant, because this is height as a function of t. And if you've worked in these wetting problems, even in the non-equilibrium ones, I mean, this is what happens if you cross the phase boundary. So we could actually check that this is wet, if I can, and then if you cross the phase boundary, then this interface moves with a constant velocity. Well, I know Park would ask me for the exponents, but if this was equilibrium, I would expect a log-log. So this is almost impossible to see in a simulation. So this is again height of film now versus bulk temperature, bulk density. As you approach the bulk density, this seems to diverge. Miku says this is compatible with a log-log, but I mean, Dan Frankel would not like to abide by it. Certainly it diverges, and it seems to diverge at a very well-defined density, which is, as far as we can tell, all of these are simulation results, is what we've calculated previously for the bulk densities. So this is the story for the wetting. So no wetting transition, at least no wetting transition on the coexistence curve. And these exponents I was talking about, for those who know, it's the complete wetting. So if you're above the wetting transition, as you approach the bulk density, again, these things should diverge with a well-defined exponent. And we can only say that we cannot calculate it very clearly. Finally, and this is work which is not published because we frankly still need to do a lot more work. This is now how rough is the interface. So you can measure the interface. There have been reports in the literature that the interfaces of these active Brownian particles, just like the capillary wave spectrum, or they sort of scale like the Edwards-Wilkinson, like the equilibrium one. And I frankly don't believe it. But when we try to do an experiment, numerical experiment, so we start with a stripe of dense active matter, and then we just relax it to the bulk. It will go on its own to try and relax to the bulk vapor and liquid density. So this is a relaxation experiment. And the interface, when we measure the roughness, looks very much Edwards-Wilkinson, much more than KPZ or anything else. And this is okay. This is only 1 decade maybe, and so these results. But not only us. I mean, other people are Christina Marchetti and even Hartmut Lowen saying this, and I cannot for the life of me understand why this should behave as a capillary wave or equilibrium Edwards-Wilkinson dynamics. Okay, and just the most surprising thing was we said, well, what happens now if instead of a relaxation experiment, what we do is we pump in particles, because we now have this wonderful trick or ensemble. It doesn't cost us very much to keep pumping particles into the system, and we see how the film grows. And I don't know what I would expect, but we found that this is quenched Cardar Parisian Zang. Okay, do we understand this completely? No. But I think this, well, let me thank, well, Rodrigo Coelho is not in this work, he's in the work, but Cristóvão, Micola, and Nuno Araújo. And let me go back to what we really, but I think the community itself does not understand completely. Although this looks very nice, this MIPS phase diagram for active Brownian particles, there are reports in the literature, and I'll finish with this, that this is not really like the quorum sensing phase separation. That in fact what happens, and if you look at these are not good resolution, but this liquid is very bubbly. And there is, of course, some work by Mike Cates, his group and his team, that active Brownian particles probably don't phase separate in this simple way, but they produce a bubbly liquid. For those of you who worked in microemulsions like me, it's just like you have a phase which has droplets of the other oil in water, for example, and then an excess phase of water or oil. And so if this is the case, that might explain some of these strange results, because these bubbles, and again, you know, something related to the work of Paco, this is not the same for vapor bubbles in liquid or liquid bubbles in gas. It's different. So the bubbly liquid is really a liquid with gas bubbles. And so this probably is showing that there is something, there's a beautiful PRL from last year, or this year, where they actually redid these calculations for a model which is very similar to these, and they seem to confirm this bubbly liquid picture. So Cristóvão has some ideas that some of these bubbles, because they have very different dynamics, maybe they act as the dynamics, there's separation in scales, and maybe that can explain these quenched Cardar Parisian Zang. I quite frankly don't know at all at the moment. Okay, I think I've more or less used my time, and this is for those of you in Granada. I want to finish with this slide. I've thanked everybody, and then I want to ask you if you know who the lady is. And I'll give you a hint. she has something to do with the building next on the right, not the Alhambra, although I'm sure she slept there sometimes, but with the other palace. Thank you very much, Pedro, Paco, and everybody. And I'll tell you who the woman is if you don't know.
Thank you, Margarida, for an interesting and entertaining talk. Now, time for questions.
Oops.
Meanwhile, Margarida, what is the hope to have experimental confirmations of your studies?
Well, let's if you talk about the very last thing, the active Brownian particles, there are experiments where they see some clustering and even phase separation, but it reminds me very much of, this is my timer. It reminds me very much of the time when I started, that the simulations were done for hundreds of particles, because some of these experiments are really for hundreds of particles at best. So some of these effects that I was talking about, you can only see them for much, much larger systems. So for the active Brownian particles, I don't see I mean, they exist, you can make them, but you can make them in limited numbers. And so some of these things, I think they will not be checked or discovered by experiment first. I think you need to do some thinking. If I go back to another situation where for the active particles, you have new phases like active turbulence. For those, there are lots of experiments, because bacteria really seem to exhibit some of that behavior, and you can study much larger systems. Of course, active turbulence, it's a very difficult problem, numerically or experimentally, but I see more chances of realizing in large systems these new phases than for the active Brownian particles, although one day maybe, I mean, and if you think of the sheep and the goats and so on, yeah, you can have maybe even in Australia thousands of sheep and goats, but I don't think we're at the verge of resolving any of these problems experimentally. But I think they pose some very deep questions that I don't think we understand. I mean, maybe Mike understands more than in his group, but they're still open. They're still open.
We have a question by Sadiq Ossi.
Hello, can you hear me?
Yes.
Yes.
I found it very interesting. It's not my field, but I'm a biologist, and I would ask whether is there any analogy or a kind of molecular biological molecule that could resemble what you call active colloids, active molecules?
Well, yes. I think, as I was saying, the thing is, there are many. I think there are many biological systems on bacterial systems that exhibit a different type of new phase, which is this active turbulent phase, where they sort of swarms of bacteria. There are also the work on microtubules and so on. It's also on that line. They're even smaller than the bacteria, and they have this pneumatic or active pneumatic type of behavior and active turbulence. Do I know any microorganisms that are as stupid as these active Brownian particles? Well, some bacteria, I've seen some pictures, but I don't think I've looked at the results. I've seen some pictures of growth of bacteria in agar or some other, where the bacteria go after the food, and so you can make them sort of, you can induce this type of directional motion rather than just too random, because if it's too random, you'll get into the if there is fluid, but they usually need fluid to be you usually get into the active turbulent regime. So I've seen some pictures where the authors claim that under certain conditions, bacterial films can grow resembling these MIPS, because when you see the growth, you can see regions with lower density and with higher density of bacteria. And so they seem to self-organize in some sense into regions of large and high and low densities. But I wouldn't say this is the most obvious thing. Many of the systems that I was mentioning and many of the people, the experimentalists are working, are, I didn't tell you how they did those particles, but if you have a colloid, it's usually they coat one half with something that reacts either to light or to some chemical, and through that they can get energy to self-propel.
Okay, I was thinking about small macromolecules inside the cell in the gel cell phases, where, as you know, there are certain regions of cells,
Yes.
think of bacteria, with special structural features that we don't know how do they assemble. But it's easy to think about microtubules with nanomachines, and those are very defined structural features. But there are some kinds of molecules and signs precisely that they have special locations, but we don't know why they are in that part of the cytosol, for example, but they are located in their space specifically. And if we somehow there's some chaos into the cell, when disorganizes the cell chemically, for example, by a detergent or an amphipathic compound, functions are almost totally lost, but without destroying the molecule, just modifying the shape they organized into the space.
Yeah, yeah. You know, the biological systems seem to have a little bit more, because let me put it this way: the self-propelling mechanism will determine whether or not, and the fluid where your particles are, will determine whether or not you get this active turbulent state rather than this simpler, I would say simpler, MIPS or motility-induced phase separation. And so I'm afraid most of the literature I know about biological systems is more on the other side, on the side of the swarms of bacteria and active turbulence. But yeah, it would be nice if there are other systems where you can find some of these. I'm being maybe a little bit negative, because there are other systems, they're not biological necessarily, but there are other systems where you can make, for example, I mean, let me be really stupid, but it's, what you need is that these particles, they take energy at the individual level and they're not driven. So it's not the field that is driving them. So for example, if you shake granular things, you can get some of these effects. Even if you use electrical fields, alternating electric fields, you can get textures in liquid crystals that will have this kind of motion and so on. But handling bacteria without killing them is more difficult. So they seem to do what they like, and they seem to usually like to get into these active turbulent states. As I said, I've seen claims that people say they do phase separate like this, but. And I have the answer from Joaquin. Joaquin Marro says, Isabel, wife of Charles I. What Joaquin does not know, probably, of course, she was Portuguese. She was deemed to be the most beautiful woman of her time. She was probably one of the best educated. And the place where she was happiest was Granada, not in the palace that the stupid husband was building because he never finished it, but perhaps in Alhambra. I don't know. But anyway, I wanted to leave. I think I've... Yes, you agree. Well, yeah, she was beautiful. She was smart. She was very smart too. She was very well educated. Those days in the Portuguese court, princes and princesses were educated at a very high level. Anyway, thank you.
No,
Okay.
thank you very much. It was very interesting.
Thank you. Thank you for the questions. I'm sorry I didn't answer them, but thank you for the questions.
Thank you, Margarida. Now we'll take a 5-minute break before we start with the last lecture of today.